Welcome to the survey of elementary principles in classical mechanics. During this series of videos, I will cover in a technical presentation the material pertaining to the first chapter of the well-known treatise Classical Mechanics, authored by Herbert Goldstein. It was originally published in 1950, taken through three major editions and some minor revisions, and to the present day constitutes an outstanding contribution to the modern physics literature. The first part of the series will mainly focus on discussing the material within the book, while the second part will focus on working out the exercises as applications of the theory. For today, I am going to cover a brief introduction and then I will go through the mechanics of a particle. Classical mechanics is the type of mechanics arising from the special theory of relativity. Fundamental physical concepts undefined for the present discussion but assumed to hold a familiar meaning are those of space, time, simultaneity, mass, and force. Mathematical prerequisites are basic knowledge of mathematical analysis for multivariable functions, so knowledge of differentiation and integration, and some basic grasp of differential geometry, mainly coordinate systems and coordinate transformations. In order to discuss the mechanics of a particle, we define the following basic quantities. By r, we denote the radius vector of a particle from a given origin, and by v, the velocity vector. By definition, it is the time derivative of the radius vector, which can be written in two equivalent ways, as the time derivative operator acting on r, or as the radius vector with a dot on top. The linear momentum vector is, by definition, the product between a particle's mass and its velocity, and by F we will denote the total force exerted on a particle from the interaction with external objects and fields. Typical fields relevant for classical mechanics are the gravitational and electromagnetic fields. The dynamics of a particle in classical mechanics is contained within Newton's second law of motion. The statement of the law is as follows. There exist frames of reference in which the motion of the particle is described by the differential equation F is equal to the time derivative of P. Or equivalently, F is the time derivative of the product between mass and velocity, or the time derivative of the product between mass and the time derivative of the radius vector. Usually the mass is constant, and therefore Newton's second law takes the more familiar form of F being equal to m times a, where a is the acceleration vector or the second order time derivative of the radius vector, which is also denoted by two dots above r. In the last form, so as a product between mass and acceleration, Newton's second law is a second-order differential equation, this assuming that f does not depend on higher-order derivatives. In its general form, it is valid in what is known as an inertial or Galilean system. The laboratory reference frame attached to the Earth is usually a sufficient approximation of such a system. In other words, for most mechanical experiments and mechanical observations, we can neglect the fact that the Earth revolves around the Sun and it rotates about its own axis. However, for astronomical applications, sometimes the reference is established with respect to distant galaxies. This is due to distant galaxies constituting a good enough realization of Mach's principle. That is, with respect to such a galaxy, we may specify an invariable direction in space, and the referential background for local unaccelerated Galilean frames of reference. For more insight on this discussion, you can read a very interesting article in the American Journal of Physics written by Percy Bregman in 1961. In the study of mechanics, of fundamental importance are conservation theorems. These are statements which indicate under which conditions certain mechanical quantities are constant in time. The first such theorem, which is immediately at hand, is the theorem regarding the conservation of a particle's linear momentum. And its statement is very simple. If f is equals to 0, then the time derivative of the momentum is equal to 0, and as such, the momentum is conserved. We can define the angular momentum of a particle about a point as the cross product between a particle's radius and its linear momentum. And we can define correspondingly the torque as the cross product between a particle's radius and the force that is applied to it. The cross product between radius vector and force is equal, by virtue of Newton's second law, to the cross product between the radius vector and the time derivative of the particle's momentum. But if we look at the time derivative of the entire cross product, so the time derivative of the angular momentum, we see that the first term is a cross product between two parallel vectors, namely the velocity and linear momentum, and as such it vanishes, while the second term is simply the cross product between the radius vector and the time derivative of linear momentum, so as such it is the cross product between r and force, or in other words it is the torque. As such, the torque applied to a particle is equal to the time derivative of the angular momentum, so the corresponding conservation theorem can be stated as if the applied torque is 0, then the time derivative of the angular momentum is 0, and as such the angular momentum is conserved. When it comes to considering energy, we can define the work done by an external force F in moving the particle between the points 1 and 2 as a line integral of the applied force along the path joining the 2 points. If we assume that the mass is constant, then the definition of work can be rewritten as follows. F is just the product between mass and acceleration, and the line element can always be written as the product between the velocity vector and a differential of time. As such, the integrand here is simply 1 over 2 multiplying the total time derivative of v squared, and then the integral simplifies to the product between mass over 2 times the difference in squares between the velocity at the endpoints of the path. By m over 2 multiplying v squared, we define the quantity known as kinetic energy and denoted by T. And what we have obtained is that the work done upon a particle by an applied force in moving it between 2 points is equal to the change in kinetic energy between the 2 points. The kinetic energy has a few interesting properties, which can both be derived from Newton's second law. First of all, assuming that the mass is constant, if we take Newton's second law and apply a dot product with the velocity on both sides, the left-hand side is, as we have observed already, simply mass over 2 multiplying the time derivative of v squared. But since the mass is constant, we can introduce this factor under the derivative operator, and as such what we obtain is that the time derivative of the kinetic energy is equal to the dot product between force and velocity. More generally, for variable mass, we can take the dot product between the linear momentum and its time derivative, and if we apply the derivative and then apply the dot product, we obtain two terms. The first one is simply v squared over 2 multiplying the time derivative of m squared, and the second one is m squared over 2 obtained from here multiplying the time derivative of v squared. As such, we can combine the terms in the time derivative of m multiplying m over 2 multiplying v squared, which is simply the time derivative of mass multiplying kinetic energy. And the result is that the time derivative of mass times kinetic energy is equal to the dot product between force and linear momentum. In a conservative system, the work done by a force upon a particle and moving it between 2 points is the same for any physical path between the chosen endpoints. And this is written formally as the statement that the line integral of the force on a closed path is equal to 0. Dissipative systems cannot be conservative. Due to what is known in mathematics as the gradient theorem, a necessary and sufficient condition for the work to be independent of path is for the force to be the gradient of a scalar function of position. So the force is equal to minus the gradient of a function v, which is known as the potential. If the work is independent of path, it can be expressed as the change of a quantity depending only on the endpoints, the quantity being minus v. So one way to write this is to take the dot product between the force and the line element, and by virtue of this definition, the result is simply minus the differential of the potential. Or equivalently, you can say that the uh, component of the force that is projected on an element of path is equal to minus the partial derivative of f along the path element, which is an equivalent statement in either forms with the definition of f as the gradient of a potential. The reference value of v is arbitrary, and in a conservative system the result is that the work is equal to minus the difference of the potential energy between the endpoints. As such, combining this result with the previous conclusion regarding the definition of work and kinetic energy, we obtain that for conservative systems, the sum between the kinetic and potential energy is the same at the endpoints of the path, or for a conservative system it means that it is the same for any point along the path. Therefore, the theorem regarding the conservation of the energy of a particle states that if f is equal to the minus the gradient of a scalar function, then the time derivative of the sum between kinetic and potential energy is 0, or in other words, the total energy is conserved. If the potential depends both on position and time, the work is no longer the potential difference between the endpoints, since the potential also changes in time. A total energy may still be defined, but it is no longer conserved. In summary, we have constructed a framework of classical mechanics for a single particle by defining Galilean reference frames and by stating Newton's second law of motion. We have defined the fundamental quantities and have developed corresponding conservation theorems for linear momentum, for angular momentum, and for the total energy. And in the following, we will generalize the above results to systems of many particles. I want to thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.